we have what is called, for Unit 7, something brand new that we've never seen before called a system of equations. Okay? Now, notice that in the title it says we have the word system. What does a system kind of mean? A group of things that are used together, right? So we're actually going to be working with more than one equation here. Okay? There are going to be 3 methods to solve these things, and today we're just doing the first method, which is using a graph. Okay, so let's first define what a system of linear equations is. Really quickly, what does linear mean? Line. Okay, so we're just working with lines here, okay? No parabolas, nothing else. Okay? So the definition of a system of linear equations is 2 or more linear equations that are grouped together. Okay, so there's 2 or more. All we are going to be looking at right now, all we are going to be working with in this unit is 2. Okay, but there are systems, when you get to Algebra 2, you're going to start working with systems of 3 equations. Okay, in Algebra 1 we just work with 2. Okay, so we are also looking at the solution to the system. And a solution is any ordered pair in a system that makes all the equations true. Okay, so remember how in Unit 6, on the test we just took, if they ask for a solution, we plugged in X and we plugged in Y and we checked for a true statement? We are going to do the exact same thing here, except we need to get 2 true statements. It needs to be true for both equations. Okay? So how do we solve by graphing? There are 3 steps here. Step 1, we are going to graph both of the equations. So we're going to graph both equations on the same coordinate plane. So we're going to graph both of them on the same graph. Coord. There's an R after the 2 O's. I got ahead of myself. C-O-O-R-D-I-N-A-T. Coordinate plane. Okay? And the solution is where both equations are true. So it's going to be the point where both of the graphs intersect. So we are looking for the point of intersection. And we are going to write our solution as an ordered pair. Okay? So, we graph both of them. We have to find the point where they intersect, and that point is our answer. How many times do 2 lines ever intersect? Just once. So how many solutions do you think each system has?
1.
Just 1. So each system has only 1 solution. Always. Okay? So example 1 asks us, is -2, 3 a solution of each system? So we're not graphing yet, we're just plugging in. So what I'm going to do, and the way I like to do these, is I do each one individually. So I'm going to do them in different colors so we can tell them apart. And I actually, just like we did during finding, when we factored and we were solving, I draw a line down the middle to separate my work, just so that I don't get everything confused. So we're going to do 1 equation on the left side, check that point, and 1 equation on the right side, check that point. Okay? Alright, so we are going to plug in -2 for X and 3 for Y. So for the first equation, we would get 2 times -2 plus 3 equals -1. That's what we're checking for. Okay, what is 2 times -2? -4.
So you're just writing yes or no for the question.
Yep, so these are just going to have yes or no answers. And what is -4 plus 3? Negative 1. Is that a true statement?
Yes.
Yes, it is. So far, we're good, right? Are we done?
Yes.
No, we have to check the other one as well. It needs to be a solution for both. So this one is just x equals negative 2, so what's the only number I have to plug in?
-2.
So negative 2 equals negative 2, true?
Yes.
Yes. So is that point the solution to the system?
Yes.
Yes.
But what happens if you get one true and one false?
Well, let's do the next one and see what happens. Okay? Alright, so the next one is 2 more. We are still checking the point, negative 2, 3, so the point has not changed. But we have 2 different equations, so let's do the first one. Y equals negative x plus 1. I'm going to plug in 3 for y, so I get 3 equals negative, and x is negative 2 plus 1. I have minus and negative, so what happens? Both become positive, so this is 3 equals 2 plus 1. Oops. And 2 plus 1 is? 3, so that's a true statement. Now let's plug in negative 2, 3 to the second equation. So I get 3 equals 1/2 times negative 2 plus 3. All I did was plug it in so far. Okay, 1/2 times negative 2. What does that give me? It does reduce. 2 goes into 2 negative 1 times, so I get 3 equals negative 1 plus 3. So 3 equals, what's negative 1 plus 3?
2.
Positive 2. Is that true? No. So it was true for the first one, not true for the second one. So is it a solution to the system?
No.
No. So our answer is just no. Okay? It needs to work for both, or it's not a solution. If it works for one and not the other, that's not good enough. You always plot the y-intercept first. So we plotted the y-intercept at 3, and then we count the slope from that point, right? Up 1 over 1, up 1 over 1. So we did 3 points here just to make our graph more accurate. So draw a line and try and make it as straight as possible.
Do you have to make it that long, or?
It has to go across the whole graph. Okay? Because you need to make sure that they will intersect. Okay? So plotting the second line, what's my y-intercept there? Negative 4. So let's count down. 1, 2, 3, 4. And my slope this time is negative 5, positive 2. So I'm going to go down 5. 1, 2, 3, 4, 5. And to the right, 2 spaces. But I ran out of room to plot my third point. So what could I do? You could do it off the graph, but that's not going to be super accurate. Julia, what else could we do? Very good. I can go back to the point that I graphed the first time. And what if I attach the negative to the 2 instead of the 5? It's still going to be the same slope, right? So let's instead go up 5. 1, 2, 3, 4, 5. And to the left, 2 spaces. 1, 2. My slope, I'm still making a straight line, right? So let's connect those. Make it as straight as possible. And does anybody see my point of intersection?
The
Negative 2, 1. What I would like you to do is circle it, that point of intersection. So what is the solution to this one? Negative 2, 1. That's your answer. So I want you to do example 3 by yourself. It's not as tricky as it looks. I have 2x y equals 2x is my first one, and y equals 3x is my second one. What's the y-intercept of the green one? Well, if it was a 1, I would say plus 1, right? It's not there, so it's 0. So write in plus 0 if you want to. That is only for multiplication. Because if it wasn't there, if it was 1, it would say plus 1, right? If it's not there for this, it's 0. So what's the y-intercept for the blue one?
0.
Also 0. What's the slope of the green one?
2.
2 over
1.
1. And what's the slope of the blue one?
3 over
3 over 1. Will you guys graph that right now, both of those lines? Alright. So, the y-intercept of the green one is 0, so we're just going to put a point at 0, 0. My slope is 2, so I'm going to go up 2 and over 1. And then from that point, I'm going to go up 2 and over 1. Okay, so there's my line. Okay, my blue line, the intercept is also 0, 0, but my slope is 3, so I'm going to go up 3 over 1, and then from that point up 3 over 1. So that line is a little bit steeper. Okay. So where's the intersection?
0, 0.
It's at 0, 0, so our solution for this one is 0, 0.
Wait, what makes it 0, 0?
Because it's at the origin. They both intersect at that point.
Where they intersect is
Where they intersect is the
I know, but
answer.
how come they intersect at 0, 0?
There are 2 exceptions. Every system has only how many solutions? 1. There are 2 exceptions though. The 2 lines could have no solution or infinitely many solutions. Okay, so let's look at this.
Is that like infinity and beyond?
Well, where do you think, it's like infinity and beyond, yep. Where do you think, what types of line do you think would have no solution? Colton? Parallel lines. If the lines never intersect, there is no solution. The lines never intersect. Okay? How could you check that? How could you check if they're parallel without having to graph? The slope. Slope should be the same. Okay, I'm going to write next to this in parentheses, write parallel. So that we know that if 2 lines are parallel, there is no solution to the system. Any ideas as to when there would be infinitely many solutions? Matthew? If the 2 lines were the same, because they'd be right on top of each other, right? Every single point intersects. Okay, so if the lines are the same, there are infinitely many solutions.
I've never heard that word before.
Okay? So if the lines are the same, there are infinitely many solutions. If they are parallel or never intersect, there are no solutions. Okay?